welcome you in the lecture series of Basics of Communication Engineering. It is tutorial 6th based on lectures 15, 16 and 17. Now the question first is, find the figure of merit of an AM system when the depth of modulation is 100%, 50% and 30%. We know the figure of merit F, it is equal to m square p by 1 plus m square p. And now first case, when m is 100%, 100% means m is equal to 1. So the figure of merit in this case, it will be p upon 1 plus p, where p is the average power of the modulating signal. Now if I consider the modulating signal xt is a single tone, means cos 2 pi fmt, then the power of this signal, it will be, the amplitude is 1 here, so the power is 1 by 2. And so the figure of merit, it will be p upon 1 plus p, or you can say 1 by 2 plus 1 by 2, so it will be 1 by 3. Now if modulation index is 50%, m is 50%, this means m is 5. Now figure of merit, m is 0.5. Now figure of merit, it will be 0.5 square p upon 1 plus 0.5 square p. So it will be 0.25 into 1 by 2 plus 1 plus 0.25 1 by 2. It will be equal to 0.125 divided by 0.125 plus 1. So it will be equal to 0.111. Now if modulation index is 30%, then m is 30%. This means m is equal to 0.3. And now the figure of merit, it will be 0.3 whole square p upon 1 plus 0.3 square p. So if for the single tone, the p is 1 by 2, so it will be 0.3 whole square 1 by 2 upon 1 plus 0.3 whole square into 1 by 2. So it will be equal to 0.04306. Now next question. An AM receiver operating with the sinusoidal modulating wave and 80% modulation has an output SNR 30 dB. What is the corresponding carrier to noise ratio? We know for AM system with modulation, the post SNR, the post SNR for AM system, it will be equal to AC square m square p divided by 2 FM N naught. If the modulating signal is single tone, means xt is cos 2 pi fmt, then the power of the signal, means expected value, it will be 1 by 2. And here given the modulation index m is 80%, this means m is 0.8. Then the post SNR is given 30 dB, or you can say this post SNR in normal form, it will be 10 is to the power 30 by 10, or you can say 10 is to the power 3. So post SNR, it is given 10 is to the power 3. So using this equation, we can have AC square m square p by 2 fm n naught, and it is equal to 10 is to the power 3. So from this we can calculate AC square by 2 fm n naught. It is 1000 AC square. It is 1000 by 2 fm n naught 0.32. So it is. Now the carrier to noise ratio. The carrier to noise ratio CNR, carrier power AC square by 2 and noise power BT n naught, or you can say AC square by 2 into 2 FM n naught, because transmission bandwidth in AM twice the modulating frequency, and it will be equal to AC square by 2 into 2 FM n naught. And we know this AC square by 2 FM n naught we have calculated, it is 1000 by 0.32. So we can write it will be equal to 1000 by 0.32 into 2, or it will be equal to 1562.5. So this is SNR, and SNR in dB we can calculate by taking log 10 of this value 1562.5. So it will be equal to 31.9 dB. Now, question third. An AM transmitter is to transmit a message signal having a bandwidth of 20 kHz and an average power when normalized such that the value of mod xt less than equal to 1 of 1 over a transmission channel characteristic by an additive noise of two-sided power spectral density of 0.5 into 10 is to the power minus hertz. So here noise power spectral density is 0.5 10 is to the power minus 15, and total transmission loss is 100 dB. If the modulation index m is equal to 1, determine the average transmitted power if the destination SNR or post SNR is to be 10 is to the power 4. So post SNR is given 10 is to the power 4. We know the figure of merit is the ratio of post SNR and reference SNR for the post and reference SNR ratio. And you know the figure of merit, this is given as m square p by 1 plus m square p in case of AM. Here, if I consider the reference SNR, it is equal to gamma. Then the post SNR for AM system, it will be equal to m square p by 1 plus m square p into gamma. Here we have normalized the power equal to 1. So P is 1, then it will be a post SNR. It will be 1 by 1 plus 1, and because M is given, it is also 1. So it is gamma by 2. So the post SNR is gamma by 2. Or you can say the post SNR for AM system, in this case it is 0.5 gamma. We know the pre-SNR, it is for AM system, average power of AM wave divided by average power of a noise in message. So average power, received power, PR by N naught FM, and we can write it as PR by, we have given the power two-sided power spectral density N naught by 2, it is 0.5 into 10 is to the power minus 15. You can see in this question 0.5 10 is to the power minus 15. So n naught, it will be 10 is to the power minus 15, and FM is 20 kilohertz. So it is 10 is to the power minus 15 into 20 kilohertz. So it will be received power divided by 2 into 10 is to the power minus 11. And here we have considered the noise for the message. So this SNR, reference SNR, can be considered as the reference SNR, pre-SNR. So it will be the reference SNR, and we know we can have the reference SNR is gamma. So the value of gamma is PR by 2 into 10 is to the power minus 11. So the post SNR for AM system, it will be 0.5 into gamma. From equation first, it is 0.5 PR divided by 2 into 10 is to the power minus 12, and from this this is given in the question, it is equal to 10 is to the power 4. So from this equation we can find the received power, it will be 4 into 10 is to the power minus 7 watt, and total loss is given 100 dB. So in simply we can say loss is 10 is to the power 100 by 10, or 10 is to the power 10. So the transmitted power, you know, it is received power into losses, and losses are 10 is to the power 10. So it is 4 into 10 is to the power minus 7 into 10 is to the power 10. So the transmitted power is 4 kilowatt. Now the next question is the equation for FM wave. It is XCFT. It is tan cos 5.7 into 10 is to the power 8t plus 5 sine 12 into 10 is to the power 3t. Calculate carrier frequency, modulating frequency, modulation index, frequency deviation and power dissipation in 100 ohm. We know the standard wave for FM, it is AC cos 2 pi FCT plus MF sin 2 pi FMT. So after comparing these two equations, we can have the carrier frequency Fc. So from this, the Fc will be, it is 5.7 into 10 is to the power 8 by 2 pi. So it will be 90.71 megahertz. This is carrier frequency, and modulating frequency FM, it will be from here, this is 12 into 10 is to the power 3 by 2 pi, and it will be equal to 1.909 kilohertz. Now modulation index, from this comparison you can say that modulation index MF, it is equal to 5. And frequency deviation, you know the frequency deviation del F, it is equal to MF into FM. So it will be equal to 5 into 1.909 kilohertz. So it will be equal to 9.549 kilohertz. Now the question is power dissipated in 100 ohm. You know power dissipated or transmitted power, it is AC square by 2R. R is 100 ohm. So the dissipated power in 100 ohm, it is AC square by 2R, and it will be equal to, AC is 10, so 100 by 2 into 100, so it will be 0.5 watts. Now next question. In the block diagram shown in figure, find out the carrier frequency, frequency deviation and modulation index at point A and at point B. Assume that at the output of the mixture, the additive frequency component is being selected. So here the frequency is added at the output of this. So at the point A, if a carrier frequency at the input of the multiplies Fc, then the carrier frequency Fc dash at this point, it will be 3 Fc, and the frequency deviation, it will be 3 into the frequency deviation at the input, and modulation index, it will be 3 into modulation index at the input of a multiplier. And the maximum frequency, you know the maximum frequency, it will be Fc plus del F, and minimum frequency, it will be Fc minus del F. And at point B, only additive component will be considered. If I consider from the oscillator the frequency is F naught, then at the mixer output, the carrier frequency Fc double dash, it is the carrier frequency at the input of the mixture plus oscillator frequency F naught. And F maximum at the mixture output, it will be F max plus F naught, and F minimum, it is F minimum dash, it will be F minimum plus F naught. And at the point B, the frequency deviation, it will be F max dash minus Fc dash. So we will calculate this at point A. Fc dash, it will be 3 into 10 megahertz, so it will be 30 megahertz. And frequency deviation del F dash, it will be 3 into del F, it is delta F, it is 10 kilohertz, so it is 30 kilohertz. So frequency deviation delta F dash, it is 30 kilohertz, and modulation index MF dash, it is 3 into MF, it is 5, so it is 15. Now the minimum frequency at point A, F minimum, it is Fc dash minus del F dash, so it will be Fc dash, it is 30 megahertz minus 30 kilohertz, 30 megahertz minus 30 kilohertz, so it will be equal to 29.970 megahertz. And maximum, it will be Fc plus Fc dash plus delta F dash, so it will be 30 megahertz plus 30 kilohertz, 30 megahertz plus 30 kilohertz, so it will be 30.030 megahertz. This is at point A. And at point B, Fc double dash, it will be Fc dash plus F naught, and it will be 300 megahertz plus 10 megahertz. So it will be equal to 40 megahertz. And maximum frequency f max dash, it will be f max plus f naught, and f max here we have, this is 30.03, so it will be 30.03 plus 10, it will be 40.03 megahertz. And minimum f minimum, it will be f minimum dash, it will be f minimum plus f naught, and f minimum it is 29.970 plus 10, so this is 39.970 megahertz. And at point B, the frequency deviation, it will be, f max minus fc dash, and it will be equal to f max is 40.03 megahertz minus fc dash, this is 40 megahertz, so this is 0.03 megahertz, or you can say it is 30 kilohertz. So at point B, the frequency deviation is 30 kilohertz, corresponding to the frequency deviation at point A is 30 kilohertz. So these are frequency deviation are same. So as we can see, there is no change in the deviation due to mixing. The modulation index will remain same. MF is 15. Now next question, given xt is equal to sine 2000 pi t, kf is equal to 200,000 pi, and kp is equal to 10. Estimate the bandwidth of xcft and xcpt, means the bandwidth of fm and bandwidth of pm. Repeat part A if the signal amplitude is doubled, and repeat part B if the message signal frequency is doubled, and comment on the sensitivity of FM and PM bandwidths to the spectrum of XT. So for the first part, estimate the bandwidth of XCFT and XCPT. So delta F, the deviation, it is KF into AM by 2 pi. Here KF is 200,000 pi, and so we can write 200,000 pi, and AM is 1 for the signal xt AM sine 2 pi FMT, so AM is 1 divided by 2 pi, so it will be equal to 100 kilohertz. So frequency deviation is 100 kilohertz. And now the baseband signal bandwidth FM, so here from here you can see the FM, it will be 2000 pi by 2 pi, or you can say 1 kilohertz. So if you know the deviation and the modulating frequency, you can easily find out the bandwidth. And the bandwidth from the Carson rules, Carson's rule, it is bandwidth is equal to 2 del f plus fm, and it will be equal to 200 plus 1, it will be 202 kilohertz. So bandwidth is 202 kilohertz for the FM case. And for PM case, the frequency deviation, it is kp am dash am by 2 pi. Am dash is the peak amplitude here in phase modulation. So phase modulation is the basically frequency modulation, but the modulating signal in this case is the differentiated version of the signal xt. So am dash is the amplitude of d by dt xt. So xt is given, it is sine 2000 pi t, so d by dt xt, it will be 2000 pi cos 2000 pi t. So the amplitude am dash is 2000 pi. So from here the frequency deviation am dash kp is 10 given into 2000 pi by 2 pi. So from here it is 10 kilohertz, and the bandwidth you can calculate now, it is 2 del f plus fm, it will be equal to 2 10 plus 1 22 kilohertz. So in case of PM, the bandwidth requirement is 22 kilohertz, and in case of FM, the bandwidth requirement is 202 kilohertz. Now the part B, repeat part A if message signal amplitude is doubled. So means the message signal xt now it will be doubled, means amplitude sine 2000 pi t. So amplitude is double, then fm it will be 2000 pi by 2 pi, it will be 1 kilohertz, and am is 2, and am dash here it will be 4000 pi. So these values will be double. So for fm case frequency deviation it will be kf am by 2 pi. So it is here am is 2 now, 2 into 2000 pi by 2 pi, it will be 200 kilohertz. And for pm case the deviation it will be kp am dash by 2 pi. Here am dash is 400 pi now, so 10 into 4 so 4000 pi, am dash is 4000 pi by 2 pi, it will be equal to 20 kilohertz. And now the bandwidth for this case, for pm case it will be 2 into del f plus fm. So for pm case the bandwidth is 2 into del f plus fm, and it will be equal to 2 into 200 plus 1, it is 402 kilohertz. And for case pm bandwidth it will be 2 into del f plus fm, and here del f is 20 plus fm1, and you can see here it will be 42 kilohertz. Now part c is repeat the part b if the message signal frequency is double. Now this time the signal frequency will be double instead of the amplitude. So now in this case xt will be sine and double of the frequency it will be 4000 pi t, and fm it will be 4000 pi by 2 pi, it will be 2 kilohertz, and am it is 1, and am dash it will be 4000 pi. When you will take the d by dt of xt, am dash it will be. So for fm case the deviation it will be kf am by 2 pi, so it will be 200,000 pi into 1 by 2 pi, and it will be equal to 100 kilohertz. So bandwidth for this case it will be 2 into del f plus fm, so it will be 200 plus 2 204 kilohertz. And for pm case the frequency deviation kp am dash by 2 pi, kp is given 10 and am dash 4000 pi by 2 pi, so it will be 20 kilohertz. And the bandwidth for this pm case it will be 2 del f plus fm, and it will be equal to 220 plus 2 44 kilohertz. So the next point is comments on the sensitivity of FM and PM bandwidths to the spectrum of XT. So we have seen doubling of the amplitude of XT roughly doubles the bandwidth of both FM and PM. So here we can see the bandwidth for FM case here 202 kilohertz. When I have increased the amplitude 2 times or double the amplitude, then the frequency it will also increase. From here we have calculated frequencies 404 kilohertz, and for the pm case frequency is 10 kilohertz, and when I have doubled then in this case frequency is 40 kilohertz. And when I have doubled the frequency, and we can see doubling the frequency of xt has hardly any effect of fm bandwidth. However, it roughly doubles the bandwidth of pm, indicating that PM spectrum is sensitive to the shape of the baseband spectrum. FM spectrum is relatively insensitive to the nature of the spectrum of the baseband signal. So this is comment on FM and PM spectrum. Next question. Design only the block diagram of an Armstrong indirect FM modulator to generate an FM carrier with a carrier frequency of 98.1 MHz and frequency deviation 75 kHz An narrow band FM generator is available at carrier frequency of 100 kHz and frequency deviation delta F is 10 kHz. The stock room also has an oscillator with an adjustable frequency in the range of 10 to 11 MHz. There are also penalty of frequency doublers, triplers and quantuplers. So you can see here FM modulator and the frequency from the FM modulator, it is 100 kilohertz and deviation is 10. And now if I will use the multiplier of 125, so with the multiplier of 125 FC will be 12.5 megahertz and the deviation it will be 1250 hertz. Now if I will use the product modulator and this with the oscillator having 10.865 megahertz, then and using the band pass filter and which is having frequency 1.635 megahertz, then I will get the frequency 1.635 megahertz and deviation is 1250 megahertz. So at this point there is no change in the frequency deviation. And after this, if I will use multiplier into 60, then the frequency FC carrier frequency at this point at the output of this multiplier it is 98.1 megahertz and deviation it will be multiplied by 60, it will be 75 kilohertz. So this is our requirement to generate the frequency carrier frequency 98.1 megahertz and deviation 75 kilohertz. Now next question. A carrier wave of frequency 100 MHz is frequency modulated by a sinusoidal wave of amplitude of 20 volts and frequency 100 kHz. The frequency sensitivity of modulator is 25 kHz per volt. So part A, determine the approximate bandwidth of FM signal using Carson's rule and repeat your calculations assuming that the amplitude of modulating signal is doubled. So in this case amplitude is doubled, and repeat the calculation assuming that the amplitude of the modulating frequency is doubled. So in this case frequency is double and in the second case amplitude is double. So for the part first, determine the approximate bandwidth. So you know here delta F deviation is kf into am and you have given kf is 25 and am is 20 into 10 is to the power 3. So by this you will have 5 into 10 is to the power 5 hertz, or you can say 0.5 megahertz. So frequency deviation is 0.5 megahertz, and the bandwidth, now in this case the bandwidth for this FM it will be 2 delta F plus FM. So here it will be 2 into 0.5 plus 100, so it will be 201 megahertz. Now the second case, when I have increased my modulation or I have doubled, so you know delta F it is kf into am and am is doubled, so it is 25 into 40 into 10 is to the power 3, so it will be 1 megahertz, and the bandwidth is 2 into delta F plus FM, it will be 2 into 1 plus 100, or it is 202 megahertz. And third case, FM is doubled, here AM is doubled, so by increasing FM you know it is AM and it is 0.5 megahertz as in previous case, because this is depend on A. Now the bandwidth in this case 0.5 plus FM. Now FM is doubled, 100 to 200. So this is 401 megahertz. So you can see in the normal case the deviation is 0.5 megahertz and bandwidth is 201 megahertz. Now if I double the amplitude, there is slight change, or you can say no change in the bandwidth of the signal. But if I increased or double my modulating frequency FM, then by doubling the modulating frequency you can see 401 megahertz. This is 401 megahertz, or you can say the bandwidth is also double. So by doubling the amplitude there is no change in the bandwidth, but by doubling the frequency FM there is doubled the bandwidth. So bandwidth will also be doubled by doubling the frequency, but there is no change in the frequency if double magnitude which is given. So this is the end of this tutorial 6, and in the next lecture we will discuss about the sampling theorem, pulse modulation. And till then, thanks for listening this tutorial. Thank you.